Sunil?
Hi, Sanjit. How are you?
Hi, good. How are you?
I'm doing good. Thanks for accepting our invitation and
Of
agreeing to
course.
give a talk here.
Delighted to be here.
So Aditya will be chairing the session, Aditya Thakur from UC
Okay.
Davis.
Okay.
So I expect that he will be joining soon. Yeah.
All right. So I think I will then share my screen once Aditya arrives, right?
You can, yeah, we have time. We have another 10 minutes. Yeah. So we can start the sharing after 5 minutes. So
Okay.
it works, right? You can try it out whether it works.
Yeah, it should. Okay, let's just do a quick try.
Yeah, you can try it out.
Okay. Can you see it full screen?
Yes, it's good. Yeah.
Okay, excellent. All right. So I'll come back and share screen in about 5 minutes.
Yeah, sure. That's good. Yeah. Thanks. Hi, Aditya. Thanks for joining. Can you hear me?
Morning.
Hi, good morning.
Oh,
Thanks
good
for
evening.
waking
Sorry.
up. Yeah. So, thanks a lot for joining early morning. Yeah. So Sanjit is already online, so he tested the slides, so everything seems fine.
Okay, excellent.
We'll have about 7 minutes. Yeah. So
Perfect.
there was an invited talk by Sanjeev Arora, which just got over like 15 minutes back. So there are some
Perfect.
people on gather, so they should be back in about 7 to 8 minutes, I guess. Yeah.
Excellent. Yeah.
Yeah. Thanks.
Great. Yeah.
Thanks.
Hi, Aditya.
Hey, hi. How are you?
Good. Good to see you.
Yeah, same. So,
Should I go?
do you know? Oh, sorry. I was just going to ask you. Oh, sorry again. Go ahead.
Race conditions. No, I was going to ask if I should go ahead and share screen.
Sure. Yeah.
Okay.
I think we have probably 3-4 minutes before we start, but yeah.
Okay.
Yeah. My question was whether you wanted questions during the talk, or should I interrupt you in case I see questions? Will you pause, or will we just have questions at the end?
I'm logged in twice, and so from 2 computers, and so I can check the chat, but feel free to pause. I'll probably pause in the middle a couple of times and ask for questions. So okay, let's just do it that way.
Sounds good.
And then I'll take most questions at the end.
Perfect. Yeah.
Okay, so you can see it full screen now?
Yeah, perfect. Yeah.
Okay.
So I see people joining back in. So maybe we'll start in, say, a minute, roughly.
Sure. Yeah, I'm okay to. Yeah, we can start with the introduction, and
sure.
And
okay.
Perhaps another minute or two we can get going with the talk.
Excellent. So maybe I'll just start now introducing our speaker.
Sounds good. Thank you.
Yeah. Okay. So it's with great pleasure that I introduce Professor Sanjit Seshia. He's a professor in the Department of Electrical Engineering and Computer Sciences at the University of California, Berkeley. He received a MS and PhD in computer science from Carnegie Mellon University. So he's made contributions to numerous research areas, including formal methods, computer security, machine learning, and robotics, to name but a few. He's also received numerous awards, including the Presidential Early Career Award for Scientists and Engineers, the Alfred P. Sloan Research Fellowship, the Frederick Emmons Terman Award for contributions to electrical engineering and computer science education. He's also a fellow of the IEEE. Recently, he's been doing some very interesting work on verification of artificial intelligence, combining formal methods and machine learning and so on, which relates to the topic of today's talk, I believe, on algorithmic improvisation for dependable intelligent autonomy. So Sanjit, whenever you're ready, take it away.
Okay, thank you. Thank you, Aditya, for that introduction. And thanks to the organizers for this invitation. And thank you all for tuning in. I hope all of you are safe and well wherever in the world you are. So I'm really excited to speak about algorithmic improvisation. This is a topic that invented about a little bit more than 7 years ago. And one of the reasons I'm excited to speak about this today at FSTTCS is because FSTTCS plays an important role in the story of algorithmic improvisation. So let me set the context here. So the context is that, as we are all aware, in cyber-physical systems, which are systems that tightly integrate computation with the physical world, we are seeing increasingly the use of autonomy. So autonomous systems, either fully autonomous systems or semi-autonomous systems that interact closely with people, as you can see in the pictures on this slide. And also increasingly, we see a use of machine learning and artificial intelligence in these systems. And with this growing use of machine learning and AI, we particularly see this happening in safety critical autonomous systems. So here I've shown one very compelling application of intelligent autonomy, which is in the automotive area. So on the left, you see one of the places machine learning is used is in computer vision, in object detection, recognition, image segmentation, often using deep neural networks. And on the right, you see that this use of AI in the automotive sector is projected to only grow in the next decade. But at the same time, with this deployment, there are growing concerns about safety. We know there are numerous papers showing that deep neural networks can be easily fooled. And unfortunately, there have been accidents, including some fatal, involving the potential failure of AI and machine learning-based perception in self-driving cars. So for the last many years, my research group has been looking at the following question, which is, can we address the design and verification challenges of AI and machine learning-based autonomy with formal methods? And there's many ways in which you can do this. So on the formal modeling side, I believe that formal methods can play a very important role in precise programmatic modeling of the environments, which are often very complex, as you can see in the pictures here. It can help with mathematical specification of requirements and metrics that are crucial to specifying properties of these systems. It can help with developing scalable algorithms for verification and testing of these systems. And finally, in some cases, we can try to achieve methodologies for provably robust system design. In this paper that I have listed at the bottom of the slide, Towards Verified AI, I and my co-authors have listed our ideas and some of the early results going towards all of these topics. But today I want to focus on one particular aspect of the research we've been doing, which is randomness. And in particular, the idea that randomness plays a crucial role in the use of formal methods for autonomy. So let me explain to you what I mean by that, okay? So here's one reason to use randomness, okay, which is to achieve variety or coverage. So imagine that your task is you have a neural network that is tasked with detecting objects, for instance, in a self-driving car. And you want to systematically train and test this neural network. So one of the aspects is you have to be able to generate images that you can use for training and testing, because often collecting these images by driving around is incomplete and also time consuming. In particular, let's say you want to generate images of bumper to bumper traffic. Okay. Now, as you can see with just the 3 images on this slide, there's a huge and diverse space of possibilities, right? The different time of day, different types of cars on the road, different densities, different environments in which they drive. And the use of randomness lets you cover this space pretty well. Here's another reason to use randomness, which is really realism. So in particular, what we've seen is modeling human behavior, because humans, in one of the aspects of modeling humans is that there's a lot of randomness, right? From person to person, and also the same person over time can display very different types of behavior. And in particular, what you're seeing on this slide is an application we did to automatic control of lighting in a home when a person is away. Okay, so you can imagine this sort of thing is useful from a security viewpoint to sort of mimic that user's typical behavior, but you don't want this to be too deterministic because really human behavior does exhibit some randomness. Okay, and so this is one place where sort of random generation of controls can be quite useful. And then here's one more reason for randomness, which is unpredictability. So imagine you have a surveillance robot. The robot is tasked with patrolling a certain area, visiting a bunch of important locations sufficiently often. Now, of course, you could use a completely random route that makes the robot's location hard to predict, but it's not completely, complete randomness is not necessarily going to work because you always have safety constraints and you have energy constraints and other things like that, okay? And so that's another reason why you want randomness, but with some control. Okay, so we've seen three applications here of the use of randomness in autonomous systems of different kinds. And we've seen that randomness is really essential for all of these systems. But as I hinted, they should also satisfy formal specifications, right? So it's not sufficient for the behavior to be just random in an unconstrained way. So in the case of the home lighting controller, you might want that the lights can change randomly, but it should use less energy. For the case of the image generation, you want the images to be physically realistic, right? Satisfying constraints like the objects must not intersect. And in the case of the random patrolling drone, you have safety constraints, like it shouldn't collide with other moving or stationary obstacles. Okay, so the question here is, how do you develop algorithms to design systems like these that need to have random but controlled behavior? All right, so so we've been working on this, like I said, for the last 7 years, and we've done published a number of papers on this. Just to mention the applications that I talked about, we have work on randomized controller synthesis that appeared at CAV 2 years ago, which is for this randomized patrolling application. We did work on this human modeling for the randomized lighting control that we published at an IoT conference a couple of years ago. And then we've done work on random generation of data for simulation-based training and testing of machine learning components, which appeared at PLDI last year. But really the connection to FSTTCS is that the theory of algorithmic improvisation was something that we published at FSTTCS 5 years ago. And this is the theory that really informs all of these other applications that I showed you. So we have a really nice connection to FSTTCS, and I'm really glad to come back and share with you all the work we've been doing since we last spoke about this. Okay, so we call this algorithmic improvisation. Originally, we had termed this as control improvisation, so I'll use both of these terms interchangeably. This is really a framework for automatically synthesizing systems, some of them reactive, that have random behavior, but which also satisfy formal guarantees. And the formal guarantees have really three forms. The first is some notion of guaranteed safety, which we provide using two types of constraints, hard constraints and soft constraints. And then also a notion of guaranteed randomness. That is, we want certain distributional properties on the output of these systems. And that's the third type of constraint, the randomness constraint. And one of the important novelties of this framework with respect to the literature in computer science and engineering is that this problem, the specification of this problem prescribes a certain kind of random behavior. So it's a little different from work, for instance, on generating random strategies for control, because in this case, we want certain distributional properties in addition to satisfying these hard and soft constraints. All right. So before I get into the rest of the talk, I want to acknowledge two people with whom I've taken this journey in algorithmic improvisation. So on the left, I've shown my colleague, David Wessel, my former colleague, with whom I actually started this journey more than 7 years ago. So David was a professor of music at Berkeley, and it was really a conversation with David on improvisation by musicians that started my work on this topic. And it was really a wonderful collaboration, although far too short, that led to all of this work. And then the other person is my student, Daniel Fremont, who finished his PhD last year on this topic. So a lot of the results I'll talk about today, almost all of them have been led by Daniel, and he's now an assistant professor at UC Santa Cruz. Okay, so here's the outline for the rest of my talk. So I'll first tell you about this problem, control improvisation. I'll define it and give you a few motivating applications. Then we'll dive into theory. So I'll talk about the theory of control improvisation, how you can achieve efficient algorithms for different instances, and some hardness results that we have. Then I'll focus on one application of improvisation, which is in the design and analysis of machine learning-based autonomy. And then finally, I'll conclude and talk about some exciting future directions. Okay, so let's get started. Let me tell you about this problem. Okay, so here in this video, I'm going to show you the actual implementation of this robotic patrolling problem that we did. So this is implementing the algorithms that we published in our CAV paper on an actual robotic platform in a lab. And what's happening here is you see a drone here on the bottom right currently, and you see all these white squares that have numbers. So this one on the left, which is numbered 0, is like the home base where the drone has to return periodically to charge itself. And then its task is to visit these squares, visit each of the squares sufficiently often. Okay, but it has to do this in a very random way. So you can see here that the drone visits these 4 squares. It goes back to the home location, and then it'll go and visit another square. But you'll see each time it takes a route which is very different from the ones that is done before. Okay, so that is an example of improvisation at work on real robotic platforms. Okay, so that's the application. You want to patrol an area in a way that is unpredictable. And what does that mean? It has to visit certain locations. In this case, in this toy example on the right, the red circles are 4 locations it has to visit sufficiently often. But obviously, all of these platforms have energy constraints. Therefore, it must take a route that is close to the shortest one. And then finally, it should not always take the same route, right? This is the part that is has to do with hard to be able to predict, right? So for each of these constraints, they have a certain nature, right? The first one is a hard constraint. The second one is what we call as a soft constraints, because you want to be close to the shortest route, but it doesn't really impose a hard constraint on the behavior. And the final one is what we call as the randomness constraint, which is a distributional property. Okay. Similarly, in the example that I showed you earlier, synthetic data generation, we have hard constraints like the objects should not intersect. We have soft constraints, which are notions of similarity. So you want to generate these images that, although they are being generated synthetically, you want them to be similar to real world traffic. And then also you want diversity in the data set, right? So that is a distributional constraint. Okay, so again, for this application too, you have a hard constraint, a soft constraint, and a randomness constraint. Okay, so these and several other applications that we have looked at, we started with music improvisation, as I told you. And then we have done work on software fuzz testing, which also has these properties. The commonalities are that all of these problems can be mathematically formalized as the problem of generating sequences subject to 3 kinds of constraints. Okay? And the first is what I call a hard constraint, which means that there is a property, and every single sequence you generate has to satisfy that property. The second is the soft constraint, which is basically saying that there's another property that most sequences must satisfy, but it's okay if you break that constraint once in a while. And the randomness constraint is basically, it can take many different forms. The form that we will look at in this first section of the talk is that no sequence is generated too frequently. So there is an upper bound on the probability mass that you can put on any sequence. Okay, so control improvisation is really a precisely defined theoretical problem that captures these requirements. And as I mentioned before, the first version of this work appeared at FSTTCS. Okay, so one of the points I want to get across is we've looked at the literature, and we find that this problem, control improvisation, seems to be a fundamentally new problem in computer science. I've just given on this slide a selection of some of the other topics that have appeared in the literature, for example, in fuzz testing or uniform sampling from different formal languages or in reactive synthesis. And one of the aspects here is that it's only the control improvisation problem that has this combination of three types of constraints, hard, soft, and randomness, as well as something that extends to reactive systems that maintain an ongoing interaction with their environment. Okay, so now let's dive into the formal definition, and I'm going to use the patrolling drone as an example to illustrate the formal definition. So here you see that example here on the right-hand side. And in this example, there is a drone on the bottom left, which is the one that we want to randomly control. And there's an adversary drone on the top right. And there are these 4 red circles that the improvised drone has to visit. So what's the task? Imagine that the drone moves only in discrete steps. So it can move either one step north, south, east, or west. And it has to only run for 30 steps. Okay, so there's a finite bound on the length of the sequence. Now the hard constraints are given by a specification which says visit all the circles and avoid collisions, right? So it should avoid collisions with this adversary that's at the top right. The soft constraint is given by another specification S, which says that don't visit the same circle twice. Okay, so this is one that you can violate, whereas the hard constraint is something that you cannot violate. Okay, and then the randomness constraint is that you want to make sure that you don't generate the same route with very high probability, so you have a bound on it. Okay, so now you can think of the set of all possible sequences now is going to be sigma to the n, right? And that includes plans for this robot where it does something unsafe. It collides with the adversary drone, right? So we want to exclude those. So the set of all sequences that satisfy the hard constraints are what we call the set I of improvisations. So this is basically the intersection of sigma n with the language of H. Okay, that's the red circle. And that includes sequences like this, where you can see here that it visits all 4 circles, but it visits this top left circle twice, right? So that satisfies the hard constraint, but it doesn't satisfy the soft constraint. So the soft constraint is what we call the set of admissible improvisations A, right? So that's the set of improvisations intersected with the language of S. And that includes the sequences that satisfy both the hard constraints and the soft constraints. Okay. All right. So now we come finally to the formal definition. Okay. So what are we given for the definition of the control improviser? We're given the hard constraint H, the soft constraint S, and the bound on the length of the sequence N. And then we are also given certain parameters. So the first parameter is epsilon, which is an error probability, which is used in defining the soft constraint. So this is the tunable aspect of the soft constraint. We're also given 2 other parameters, lambda and rho. These are going to be used in the distributional or the randomness constraint. Okay, so given these 5 inputs, we're going to define improvising distribution. So this is a distribution that assigns a probability mass to every single sequence in sigma n. Okay, we'll call that distribution an improvising distribution if it satisfies the hard constraint, which is basically saying that every sequence drawn from the distribution is in I. It satisfies the hard constraint. The second one is the soft constraint, which says that the probability that a sequence that is drawn from the distribution satisfies the soft constraint that is in the admissible set A is at least 1 minus epsilon, where epsilon is our tunable parameter. And then the randomness requirement is saying that for all sequences in I, the mass associated with that sequence has to be at most rho and at least lambda. So you think of lambda and rho are the lower and upper bounds on the probability with which we can sample that sequence. Okay, so if you have a distribution over sequences that satisfy these 3 properties, we call this an improvising distribution. Okay, And now the problem instance is this 5 tuple that comprises the hard constraint, the soft constraint, and all the other parameters, 6 tuple, sorry. And we'll call this problem instance feasible if there exists an improvising distribution. Okay, and an improviser then is a probabilistic algorithm that samples from that distribution. So our goal in solving the control improvisation problem is, given this instance, we want to generate the improviser. So it's a synthesis problem. Okay, so as a very simple example, let's just assume that there are in this admissible set, there are only 3 sequences, A1, A2, A3. And then there are 2 further sequences, I1 and I2, that don't satisfy the soft constraint, but they satisfy the hard constraint. Okay, so one possible improvising strategy is if my bound on the probability mass is 1/4, and my tunable parameter epsilon is also set to 1/4, then what I can do is I can sample. So first of all, observe that I cannot sample uniformly random from A, right? Because that will put too much probability mass, or uniform random or any other way from A, because that put too much mass on at least one of these sequences. And so what I can do is I can, with probability 1/4, I can sample from inside A, one of A1, A2, A3. And then with probability 1/8, I can return either I1 and I2. And if I do this, then you can work out the math and you'll find that the probability with which we satisfy the soft constraint is going to be, at least 3/4. And the probability that we put on any given sequence is at most 1/4. Right? Okay, so that's the basic control improvisation problem. And then for CAV, in a CAV paper 2 years ago, we extended this to the reactive setting. So the reactive setting, if you look at the same example, it's the case where the adversary drone is an active adversary that is trying actively to collide with the improvising drone. Okay, and so now the change to the definition of the problem is basically that this is a 2-player game. And you have the system, which is the improviser, and the environment, which is the adversary, that are alternately picking symbols, right? And what we want is that these constraints, the hard, soft, and randomness constraints, must hold against every adversary. Okay, and so for every given play of this game, we want these constraints to hold. Okay, and so an improviser now is not just a generator of sequences, it's something that encapsulates a strategy, a random strategy. Okay, and so you can think of this as a form of reactive synthesis, a randomized reactive synthesis. Of course, this is for a bounded time horizon, but it really, it shares a lot of characteristics of reactive synthesis, but in addition, it has this property that we want to achieve certain distributional constraints. Okay, so here's an example of the RCI problem. So here, for instance, you want to visit these 4 circles, and let's say n is 30, so you want to do it in 30 moves. A soft constraint might be that, well, most of the time, you want to visit each circle exactly once. And then the randomness requirement is, let's say you want to generate, like every single trajectory should look different. And you want to use the smallest feasible value of rho, which in this case turns out to be 10 to the minus 12. So you want to upper bound the probability of any given sequence to be at most 10 to the minus 12. Okay, and it turns out you can actually solve this problem this way. All right, so now let me go and talk about the theory of control improvisation. So, when can you solve this problem and when is it hard to solve? Okay. So it turns out that the feasibility of a problem, that is when you can solve a control improvisation problem, is actually a fairly simple property just over the cardinality of these sets, I and A. It just requires them to be large enough. Okay, and here's the theorem. So if you start with a control improvisation instance like this, and in this case, for simplicity, I've set lambda to 0. Then you say it's feasible if and only if these 2 constraints hold. So first of all, the set of improvisations I should be at least 1 over rho. Okay, where rho, remember, is the upper bound on the mass, probability mass for any given improvisation. And the second is that the set of admissible improvisations, A, should be at least 1 minus epsilon over rho. Okay, and that's it. So if you have the capability to count the cardinality of these sets efficiently, then you can actually check the feasibility constraints efficiently. All right. So, so now how does synthesis really work? You take a control improvisation instance, you pass it through an algorithm that we call an improvisation scheme, and then that produces the improviser, which is the algorithm that will actually generate these sequences. Okay. And ideally, we'd like a polynomial time improvisation scheme, right? So that's going to be an algorithm which, for a certain class P of instances, and if it's given a particular element of that class, if that particular problem is feasible, it should return an improviser, and otherwise, if it's not feasible, return another some symbol like bottom. And further, you want this to be efficient. That is, the improvisation scheme S, as well as the improvisers it generates, should run in time polynomial in the size of the instance. Okay, so when can we do this? Well, what we've given in our paper is a generic improvisation scheme. Okay, so this is for any type of specification. What you can vary in the specification is basically the way in which you specify these constraints, right? You could do it with regular languages or context-free languages or other kinds of specifications like temporal logic in the reactive case. So what do you need? You need to be able to do 4 types of operations. First of all, do intersection and difference of 2 specifications. Think of specifications as sets of behaviors. You can restrict a specification to a given length. You need to be able to do that. And then you need to be able to count the number of words satisfying the specification, count the cardinality of a set, and then uniformly sample from the specification. Okay, and we know actually that counting and uniform sampling can be computationally challenging, at least in a theoretical sense. Although there's been a lot of progress on doing this approximately efficiently in the recent past. But anyway, if you can do those 4 types of operations, then there's a polynomial time improvisation scheme which basically works as follows. You first construct the specifications for the hard constraint set I, the soft constraint set A, and then the difference of I minus A. You then count them and you check these feasibility constraints. And if they are feasible, then you just have to sample from A or I minus A with the right probabilities. Okay, so that's really how this scheme works. The details are all in the paper. Okay, so what does this give us in terms of complexity results? So what we've shown is that you have polynomial time improvisation schemes when the specifications are regular languages that are given by DFAs, and this has applications in music and robotic planning. For something like fuzz testing, you can actually give those specifications as unambiguous context-free grammars, and you have a polynomial time improvisation scheme for that. But other than that, it gets hard. It becomes sharp P hard because, as you can guess, right, from the constraint that you have to count or uniformly sample. Okay, and we have a lot more results in the paper. I'm just showing you a few sort of exemplar results here. Now, of course, you can do approximate schemes. So there's been a lot of recent progress in approximate model counting and approximate uniform sampling. And if you leverage those results, then you can come up with an approximate scheme in the case where specifications can be given by Boolean formulas. Okay. Now, what about the reactive case? Turns out that's also a little similar. Now, in this case, feasibility is also, again, reduces to a counting problem, but the thing we're counting is different. So what we're going to count is something we call the width, W. So the width, W, is basically a measure of the number of ways in which you can win a 2-player game between the improviser and the environment. Okay, and the theorem we have looks very similar to the theorem we have in the non-reactive case. So we say the instance is feasible if and only if the width of this the set of improvisers is at least 1 over rho, and the width of the admissible plays is at least 1 minus epsilon over rho. Okay, let me tell you what the width is. Let me give you a formal definition of it and explain the intuition there. Okay, so the width is really the number of winning plays. Remember, you have certain hard and soft constraints that define what a win is, right? And so let's imagine that X is our the desirable set, right? That's the set of all plays that are considered to be winning, right? And now every play is going to be a combination of actions by the improviser. So the improviser strategy is sigma, and actions by the adversary tau, right? So if you fix a sigma and a tau, you get a trace W. That's one play of the game. And P sigma tau W is the probability you can get that particular trace of W. And now what we'd like is W to be an X, right? It has to be a winning play. So what we're doing here is counting the number of possible traces that satisfy the constraint X, okay? And the adversary is trying to minimize the number of such plays, and the improviser is trying to maximize the number of such plays, okay? So that basically, the output of this max-min computation will give us the number of winning plays that satisfy the constraint X, right? And so now you can plug in the hard constraint here or the soft constraint, and you can compute the widths corresponding to those. Okay, so so the algorithms for the reactive case, again, it's like I said, it's quite similar. In the case of DFAs, we have polynomial time improvisation strategies. But in all the other cases, including linear temporal logic and so forth, those are the problem is p-space hard. And actually, this is not that different from the reactive case, right? It's actually, even in reactive synthesis, you have a similar complexity. Although here we're looking at the finite horizon case. All right, so that's all I wanted to say about the theory of controlled improvisation. At this point, are there any questions?
Can I ask one question?
Sure. Yeah.
So you mentioned in the two-player version where you have a min max. So in p-space you could also consider playing against a random adversary, but in this context, does it change the complexity in some way? So you're choosing the best strategy which does well against a random adversary. Yeah, it's a good question. The question is that we consider sort of the worst case adversary, right? We want to basically satisfy these constraints against any adversary. And the question was, what happens when you have a random adversary? Although we have not actually considered that particular case in our analysis, my feeling though is that the complexity doesn't change, right? And really the difficulty of doing this stems in part from just checking the feasibility with respect to this. And you can think of a random adversary. One example of a random adversary could be an adversary who does, all they have like a uniform distribution over all possible strategies that they can take. And I think this could be actually very similar to the analysis we see for the worst case adversary. Okay. So here also you mentioned p-space hard, but it is also in p-space, right? I mean, it is also complete. That's right. It is also in p-space. You're right. Okay. Yeah. Thank you. Okay. Okay, great. So let me now move on to the next section of the talk, which is on a really compelling application, which is to design an analysis of machine learning-based autonomy. And this is actually a talk where we have a tighter connection to programming languages design and implementation, because what we realized is that it's useful to specify the problem often using a programming language. So we call this language-based improvisation. Okay, so the motivating application here is coming again from this, if you think about the domain of autonomous vehicles, think about implementing perception components like object detection, recognition, segmentation using things like neural networks, right? And how do we actually train and test these components? And how do we also verify the system that contains components like these? right? So one of the aspects here is you want to model the environment. And a scene is basically the configuration of the environment around the vehicle. So what are the objects, what are the positions, what are the colors, other attributes? And as I mentioned before, collecting real world scenes is an expensive task, but it may miss edge cases that don't typically arise when you drive around, right? So the task here is we want to generate realistic scenes automatically for training and testing, okay? So what are the types of specifications we have here? Again, as I mentioned before, we have these three kinds of constraints: hard, soft, and randomness constraints, okay? Things like objects should not intersect is a hard constraint. Things like I want 20% of the images to be at night is a soft constraint. And things like, well, I want the spacing between the cars to follow certain distribution is a distributional constraint, okay? So it's an improvisation problem. And the question is, how do we best encode these constraints? And what we found is rather than sort of coming up with formalisms and specifying these constraints separately, it's useful to put them all together in a programmatic fashion as a probabilistic programming language, okay? So that's the reason we designed this language called SCENIC, which is a probabilistic programming language for modeling environments and for data generation. So a SCENIC program defines a distribution over scenes, if you look just at static images, or scenarios, if you're looking at the evolution of a system over time. There's a number of use cases. So here's an example of a very simple SCENIC program, which is modeling the case of a badly parked car. And I will go through this program in some detail. But what you can see here is that it's an embedded DSL in Python with very readable syntax. But you know, the language itself, as defined in the PLDI paper, has well-defined formal semantics. And every time you interpret this program with a backend renderer, like in this case, we're rendering with the Grand Theft Auto game engine renderer. Every time you interpret it, you'll get a new image, and they look very different, right? We've also extended SCENIC to the dynamic case. So here you see the same badly parked car, but it has a behavior now. So the badly parked car, which you see over here, this is the ego vehicle, the autonomous car. It's going to pull into the autonomous car's path as it approaches, right? And so here with the Carla simulator, you can see that we're able to generate a variety of simulations, all of a badly parked car that will pull into the path of the autonomous vehicle as it approaches. Okay, and again, you can see that you can do this programmatically with just a very little code. All right, so now let me tell you about a little bit more about the details of SCENIC. So, and we'll relate this to the control improvisation problem that we looked at earlier, right? So a SCENIC program defines a distribution, and that encapsulates the randomness constraints. As you can see, it has readable, concise syntax. Especially, we wanted something that you can use to express common geometric relationships and agent behaviors. One of the things that SCENIC as a DSL enables is that it allows us to do domain-specific sampling based on a notion of configuration spaces. And in the probabilistic programming language literature, right, there are lots of general-purpose probabilistic programming languages, but SCENIC, being a DSL, enables certain things that we can't do in a general-purpose language. And it also allows you to add declarative constraints. Okay, and I'll tell you as we go through this example how these constraints are encoded. Okay, so now let's look at that badly parked car scenario in some detail. All right, so the first part of that program was basically saying that we're going to generate data using a backend simulator renderer that is GTA. What this does, it imports a notion of the world in GTA, right? So it has a map, it has different types of objects. We're going to look at 3 types of objects here. That is a notion of a car, the notion of a curb, and the direction of a road, right? And so here, this triangle on the left is the autonomous vehicle, okay? And this blue dotted line is the view cone of the autonomous vehicle, right? So what we're going to say is the ego vehicle, which is the autonomous vehicle, this is the vehicle from whose viewpoint we're going to observe the world, is itself a car. Now, this may not seem like there's any randomness being used here, but the car is an object that has an implicit default associated distribution. And in this particular assignment, what we are saying is sample from the distribution associated with the car object. Give me a particular instance of the car object, and let's call that ego. Okay. Then we're going to, and by the way, this also, one of the attributes is the position. So it picks a location on the map uniformly at random. So from the view cone of that location, it's going to look at the curb region, and it's going to pick a point with an orientation. So let's see how that happens, right? So if you look at the, you take the view cone, you intersect that with the curb, right? And you're going to get this dark black portion, which is the visible curb. And then we'll pick a point with an orientation, and that will be called spot. Now, all of this by default is done uniformly at random, although different objects have different defaults. Okay, and you can always change those defaults. Then once you do that, at that point, we're going to pick a bad angle to park this car at. So this is the car that is rendered at a bad angle. And we say it can be any value between 10 and 20 degrees, either left or right, uniformly at random. Okay. And then we pick the car, we put that left of that spot, offset by, this is a vector. So the X, on the X side, it should be 0.5 meters into the road and no offset on the Y, right? And so we're going to place that car left of that spot, which is the black dot, oriented at a funny angle. Okay. All right. And so for that program, once you do that, when you then render using GTA, you'll get a diversity of images where other attributes of the image can change, right? The surroundings, the time of day, etc., can change uniformly at random. Okay, so what I showed you there is there are distributional constraints, but there are also implicit hard constraints, right? So we always, when you pick a position of the car, we're going to pick it on the road. So that's a geometric region, which is a hard constraint, and we're going to pick a point within that region. Okay, so there are some hard constraints that are specified in an imperative fashion, but we can also specify constraints in a declarative fashion. So we have a require statement, and this is a soft require statement, right? So here this says that with probability at least 0.9, the distance of the ego vehicle to the parked car should be at most 5 meters. So I've taken that same scenario and just added one require statement at the end. And that can produce images like this. So it'll produce a few images that may have a distance bigger than 5 meters, but the vast majority of images are going to look like this, where the parked car is now fairly close to the ego vehicle. Okay. All right. So one of the things that SCENIC allows is domain-specific sampling, as I mentioned before. I'll give you an example of this. So the default sampling method is to do rejection sampling. So we sample a point according to the distribution with these attributes, and then we'll check that the constraints are satisfied, right? And if the constraint not satisfied, then we'll repeat the process. Now this can be inefficient, but because of the domain-specific nature, we have a whole bunch of heuristics to prune the space before we actually do sampling. So one example of this is, imagine that you're trying to place the ego vehicle next to another object, which is a taxi. You want it to be close to the taxi, less than equal to 5 meters. And you also want it to be at a funny angle with respect to the taxi, right? So it has to be, the relative angle should be between 15 degrees and 45 degrees. So if you have this, then you can think about it that it'll be hard to achieve this angle in a road, right? But it's more likely that you'll have this angle in an intersection. And so here's a map of Berkeley where using our domain-specific pruning, what we find is that only the green parts, which are the locations inside intersections, are kept, and all the red portions are discarded from the sampling, right? Because the intersections are the only places where you can have this sort of a funny angle between these vehicles. Okay, so that's one example of the heuristics we have. We have a number of heuristics that actually makes rejection sampling efficient for this particular domain. Okay, so SCENIC has been applied to a range of applications, and I will touch upon just a few in the remaining time. So one of them is in generating data, particularly for scenarios that are rare Okay, so one example of this is we found that in one of the state-of-the-art neural networks for car detection, it was doing very poorly when one car is blocking another car. So you have occlusions. And so with using SCENIC, we generated a targeted data set. We augmented the original data set with this, and we were able to improve the performance not only on the original, not only on these examples, the occluded examples, but also maintain the accuracy on the original data set. Okay. Another use of SCENIC is in a form of delta debugging. So we found that this neural network was also misdetecting cars. So here it was finding 3 cars where there was only 1. And by making small delta changes to the SCENIC program and then reevaluating, we were able to figure out what the problem was. Okay. So that's a few examples, and the details are in the PLDI paper. What I would really like to focus on in the remaining 10 minutes is the use of SCENIC with another toolkit we have called VerifAI or Verify, which is something that we've used for the design and analysis of AI-based systems more broadly. And this was published at CAV last year, but I'll just give you a quick overview. So in Verify, you take in a description of the system, a description of the environment, which is a SCENIC program, and a specification, for example, in temporal logic. And you have a variety of use cases, both in verification and debugging and synthesis. But the key aspect of Verify is this internal data structure representation, which is what we call a semantic feature space. So we take the SCENIC program and we compile it into an internal representation that then enables efficient search algorithms for verification and synthesis. And we've used this in a variety of applications. What I would like to show you now is an application in the aircraft domain. Okay, so this is a collaboration we did with Boeing on a research prototype where they were experimenting with the use of neural networks for automated taxiing. So here you're going to see a simulator that's used by Boeing in this project, where there's a plane that has to follow this center line, and it has to track the center line within plus or minus 1.5 meters. There's a neural network, there's a camera that's mounted on the right wing of this plane. And there's a neural network that takes the images from this camera that you see here. And it has to basically output an estimate of the center line tracking error, which then a controller uses to keep the nose aligned with the center line. And as you can see, it can be a challenging task because of time of day, weather conditions, the skid marks that you see here on the runway, and so forth. So the first task we did was we used SCENIC to model the environment. And in this case, we talked to the Boeing people, and they said that these are the semantic features that can vary, right? The time of day, the type of clouds in the sky, whether it rains and how much it rains, and also whether there are these tire marks on the runway. And so we wrote this SCENIC program that you see here on the right. So here, for instance, we pick a time that is any time between 6 a.m. and 6 p.m. uniformly at random. We pick, using a certain distribution, we pick that there's no rain 2/3 of the time and some rain between 25% to 100%, 1/3 of the time. And then we can, the ego object in this case is a plane, and we can place a smudge mark with certain attributes with certain distributions. The property that we're looking at is that eventually in 10 seconds, the plane has to align itself with the center line, okay, within 1.5 meters. Okay, so using the SCENIC program and then using algorithms in the Verify toolkit, we were able to find multiple falsifying runs. So this is early morning time, low light, rain, and you can see that the plane loses the center line and completely drives off the runway. Okay, in fact, this was only one of 2,400 runs that we found. So I'm sorry, one of many runs that we found. In fact, the falsifier automatically explode about 2,400 runs, and nearly half of those violated this property, right? So we found lots of counterexamples. We found, in fact, contrary to our original hypothesis, that the tire mark had no effect. The time of day ended up being the most important attribute, and the clouds were also significant. And I'll show you a plot now that explains this. Okay, so here's a plot that shows on the y-axis the so-called quantitative or robust satisfaction value of our metric temporal logic property. And so what this means is that if the value is above 0, it means the property is satisfied. If the value is below 0, it means that the property is violated. And on the x-axis, you see the variation of the property with time of day, right? So in the early morning hours, you see the property is basically always violated. Then I'm sorry, this is the median. So we have multiple runs that I've shown the median for. So in the early morning hours, it's almost always violated. In the late morning hours and the early afternoon hours, it's almost always satisfied. In the early afternoon hours, though, it's once again violated. Okay. If you actually look at the images, you get a sense of what's happening. So in the case of the early afternoon hours, you get nice clear images like this. But if you look at the later afternoon hours, you see that in certain cloudy conditions, you can see these shadowing effects. And the shadowing effects are basically tricking the neural network. Okay. And so all of this was done automatically, right? All this, the analysis was done completely automatically using SCENIC and Verify. Okay. And then one thing we did was we did counterexample guided retraining. So many of you will be familiar with counterexample guided inductive synthesis, which is a common approach for program synthesis. You can think of what we did here as an application of the same counterexample guided synthesis, but in a manner where we generate counterexample images and then add them back to the data set to do data augmentation and retraining. Okay. And so now let me play now. What I'm going to show is play synchronized videos, where on the top you have the original neural network, bottom is the retrained neural network, exactly the same environment configuration, right? But you see the top neural network, even under non-raining conditions, dries off the runway, and the bottom neural network, the retrained version, is doing actually a pretty good job of centerline tracking, right? So that shows an example of how we use SCENIC in not only analyzing and finding counterexamples, but also to do synthesis and retraining to improve the neural network and the system that that the neural network is used in. Okay, and so here's a summary of what we were able to achieve. The blue plot now is the behavior of the retrained neural network, right? And as you can see that the property is now almost always satisfied at all times of day. Okay, so let me now conclude. So what I've presented today is this new framework called Algorithmic Improvisation, which is a framework for randomized synthesis. And since the early work that we did first in music improvisation and then the theory that we presented 5 years ago at FSTTCS, we've explored a number of applications in data generation, planning, fuzz testing, human modeling, and there are some other groups that have also used this idea to do interesting work on modeling human agents in different kinds of autonomous settings. There's many applications, some of which I've been able to share with you in this talk today. And I think really formal methods can contribute in many ways to the design and verification of autonomous systems. I think formal methods plays a crucial role, and randomized formal methods, I think, will play a really important role in the design and verification of autonomous systems. There's a lot of exciting directions for the future. I think improvisation is a fundamentally new problem in computer science. So I just feel like there's just so many risk possibilities at all levels, and probably more interesting theoretical problems and applications than I can imagine. So I really invite all of you, if you're interested in this topic, I think there's a lot of interesting problems to solve here. I would love to collaborate with the community. I think that, let me just highlight 3 applications here. One is intelligent data generation for a variety of data types. And we've looked at one type of data type, but I think it can really be used for many other domains. One of the exciting applications is generative probabilistic modeling. So, modeling agents, especially we're looking at things in human-robot interaction settings where you want to model the behavior of human agents or other dynamic environment agents. And I also think from a theory perspective, the problem formalization that we've given is only a starting point. There's multiple ways you can formulate soft constraints, for instance. You can look at cost constraints. You can look at different types of distributional constraints. And so we're looking at some of these in the context of design space exploration, but I really think there's a lot of different variations to this problem that are possible. So if you'd like to learn more about our work, please go to this website, algoimprov.org. Thank you all for your attention, and I would be happy to take questions now.
Okay, thank you for the excellent talks. I think we have one question in chat from Vaishnavi, who asks, okay, yes.
Yeah, I see this. Okay, let me just read that. So the question says, are there methods for generating random data set that satisfy given safety constraints? If yes, how do they match up? And okay, let me take that first part. So yes, there are methods for generating data sets. And some of them are, let me talk specifically in the context of machine learning settings. There's a lot of work in the machine learning community on using generative models, like generative adversarial networks. These do have very interesting properties, but they are hard to control. Like you can't really specify these kind of hard constraints as we have been able to. So I think programmatic approaches to data generation are definitely, they have a plus because you can enforce these sorts of constraints. And there have been some other approaches to do this sort of programmatic generation, but they haven't used probabilistic programming languages, and they also haven't targeted the domain that we have. I would think that our work on using PPLs for this topic is one of the first. There have been other uses of PPLs for graphics, for instance, generation, but in the context of machine learning models, our use case, I think, is one of the first, if not the first. The second part of your question is, how well do the resultant algorithms perform against adversarial machine learning techniques? Okay, that's an interesting question. So adversarial machine learning is this topic, for those of you who don't know, although Sanjeev's talk may have covered some of this, is basically using techniques to find small mutations of inputs that produce undesirable output. And these are very effective in a variety of settings. And they perform often these pixel level transformations, many of which are just not physically meaningful. So what we're looking at here is semantically meaningful changes or variations in the image space. And so what we've observed is that we can make the system more robust towards semantically meaningful modifications. But the robustness issues with respect to pixel level modifications remains. And I think it's just the nature of these adversarial modifications, right? Some of them, the coloring pixels, basically is something that a human may not consider to be important, but it does affect the behavior of the neural network. So I think these are kind of orthogonal methods. What we're looking at is the more semantic adversarial analysis, if you will, and not so much the pixel level. Okay. I see there's a raised hand. Yeah. Go ahead, Aditya.
There's also another question in chat from Professor K.R. Chaudhary.
Okay.
Applications to space exploration.
Yeah, sure. So what I mean by, I mentioned the term design space exploration, right? And so the idea here is that when you do design or synthesis, right, you have a certain space of possible designs or programs. And often the space is too large for you to explore using techniques, for example, based on SAT solving or optimization. But what you'd like to do is have some sort of a sampling of the space to sample many different types of points, right? And so I think this is an area where control improvisation, algorithmic improvisation can play an interesting role. We have done a little bit of work on this. You can think of in the context of synthesis of parameters. But this is actually a very active topic in my group and in Daniel Fremont's group. And we expect that we'll be publishing about this in the couple of years to come.
Okay, so maybe Prabhat.
Yeah, so in the SCENIC program for aircraft, there was a param command. What was that? Like, what is the
param command? Okay, yeah.
Yeah.
So in SCENIC, so param is basically defining a parameter that may be sampled external to SCENIC. Okay, so SCENIC has an internal distribution, an internal sampler, but we also have this verify toolkit where if you're doing falsification, your goal is not necessarily to sample according to the distribution in SCENIC. Your goal is to find bugs, to find failures. And so for this reason, we have certain targeted goal-directed samplers in verify. And by defining these parameters in SCENIC, you basically are telling SCENIC, these are variables that I might want to sample using an external sampler like in verify. So that's what that is.
Thank you.
Okay. So we have a question from Sayan Mukherjee in chat, who's asked whether you consider real-time specifications.
Right. So do you consider real-time specifications? So in fact, in the work that we did in this Boeing case and in other cyber-physical examples, we have used metric temporal logic, which is a real-time temporal logic. And so time is quantified in this case, right? So when you say eventually between 0 and 10, you have an existential quantifier over the interval 0 to 10. So yes, the answer is yes, we have considered real-time specifications.
Okay.
I see a question.
Another question from Sanjeeva.
Yeah. So is the adversary also assumed to be sampling from the same distributions, and to what extent do you need to model the adversary in the programming language? Okay. So I guess this is in the context of, say, adversarial machine learning, right? In our analysis, that is, you'd retrain SCENIC using, you retrain a neural network using a SCENIC program, or you train a neural network using a SCENIC program, and then you test it using an adversarial machine learning approach, but a semantic adversarial learning approach. And what we found is that training using SCENIC makes the system more robust to these sorts of adversarial attacks, right? So an example of that is in the Boeing case study that I showed you, right? Where we retrained using SCENIC, using the counterexample given approach, and then we're basically continuing to apply our adversarial analysis in verify to find bugs, right? And so that gives us a way of retraining it to make it more robust. Okay.
So I have a question. So I'm sort of trying to understand what this randomness and how it relates to this perhaps some notion of predictability. Yeah. So if I have this drone that is going around and I'm an adversary, and if I can observe its behavior, can I predict what it's going to do in the next few steps, right? Yes. Say I want to rob something or whatever in GTA 5. That's and right. There's some drone going on. So randomness over some longer period of time does guarantee that you'll do different things. Mm-hmm. But maybe there are certain hard and soft constraints that might force a certain behavior. That's right. And in some sense, the scheme is less predictable. So could this be captured by the specification, or is this something?
Yeah, so it depends how you define. Different? Yeah, this is a good question. This really depends on how you define what is predictable, right? So in the work that we presented at CAV 2018, we defined predictability to be a probability with which the improviser exhibits a certain behavior is smaller than some threshold, right? So an adversary, if the adversary is trying to guess what you're going to do, the best they can do is they can guess that the probability with which something is going to happen is 10 to the minus 12 or something like that, right? So that's the notion of predictability that we use there. And yes, in fact, the CAV 2018 paper gives an algorithm to achieve that. Also, but of course, the important thing is you might specify a certain threshold. You might say, can you do it with 10 to the minus 15? And the algorithm will come back and say, no, that's not feasible, right? So, but this sort of specification is something that we can handle. And of course, I think it's what's interesting is you can try to change that notion of predictability, right? So you can say, well, it's not just that I want to upper bound the behavior, but I have a property, right? And the probability with which that particular property holds has to be bounded. So now you can experiment with different types of these sorts of randomness specifications. And I think some of them can be reduced to the problem we considered, and others will be new. And I think those are new reactive control improvisation problems that remain to be solved. Okay, any other questions? I see another raised hand from Prabhat. Is there a question? I'm sorry, I'm not able to hear a question.
No, there is no question. I did not load the hand. That's why it was saying.
I see. All right. Well, if there are no further questions, thank you all again. Thank you for all the questions. And if you're interested more in this topic, please do visit this website at the bottom, algoimprov.org, and I'll be glad to hear from you as well. Okay, thank you.
Thanks a lot, Sanjit, for the wonderful talk. I just had one short comment. This is the final session of the conference, so thanks everyone for joining. Hopefully, we'll see you all in Goa next year.
All right, thank you.
So Sunil, maybe we should thank the organizers.
Yes, indeed. I mean, this entire setup wouldn't have been possible without the hard work done by the organizing committee. So they did all the work of actually getting this show on the road. So we thank the organizing committee for making this virtual conference possible. And we hope to see the organizing committee in person next year.
So maybe Bhaskar wants to single out some people.
Yeah, we had nearly there were 15 volunteers supported us, and we had 3 of our office staff supported, and so we had and I got a lot of help from Kumar as well about the Zoom. I mean, I had a lot of issues, and Kumar, I called Kumar every week and to clarify a few issues in Zoom and on. So I got a good support, and so almost I was talking to Sunil last 1 month, every 1 hour. I was talking to Sunil, and Sunil also helped me a lot. And so hopefully next year it will be on campus here, and I'm looking forward for that. Thanks.
Yeah, we're also looking forward.
So thanks to Bhaskar, Amal, and Srijit, and all the other organizers, and also Sunil and Nitin for the putting together the program, and all the workshop organizers. So maybe we should just give everyone a hand.
Okay. See you guys.
Okay.
See you. Bye.
Thanks, Malvina.
Do we still have the gather space?
Yes, we do.
Hi, Dietmar.
Hey, Deepak. Actually, you still get letters here in LSV.
Oh, yeah, I think maybe from the bank.
Yes. You have like 23 euros left. Every letter you have 10 cents less. In like 23 months, you should show up.
Yeah. Maybe I took an overdraft before leaving.
No, it's fine, it's fine. I took it with me, but as long as it's not negative, I don't bother you.